Hello everyone, welcome back to our second day of graphing rational functions. And today we're actually going to put things on graph paper and we're going to try to do the best we can to draw an accurate graph of a rational function. Now yesterday we talked about, or last class I should say, we talked about the parent function and looked at what that graph looked like. But for today, we're actually going to look at the different ways that you can see rational functions show themselves. We learned about asymptotes and zeros of rational functions in our last section. Today, we're going to add one more term to that, and that term is called wholes. So we're going to talk about what a whole is in reference to graphing a rational function. So to do that, rather than starting with the definition, I'm going to show it within our first example. And so our example here, you see the directions. It tells us identify all zeros, vertical asymptotes, and wholes, and sketch the graph. So to do that, we're going to follow the same things that we did last time. Last time, you started to find all zeros and vertical asymptotes by factoring. The top can't be factored. The bottom factors to x minus 2 times x minus 5. Because negative 2 and negative 5 add to 7 and multiply to 10. And so now we need to come up with our values that represent our zeros and our vertical asymptotes. Well, we said what makes the top be 0 makes the whole function be 0. What makes the bottom 0 makes the function undefined, and vertical asymptotes represent undefined values on the graph. So when we go to actually now create this graph, we're going to have an issue. And this came up in your homework the other day, and I hope a couple of you recognized it, that we're doing something confusing here. And that's because I said 5 is a 0. So that means the point 5 comma 0 should be on your graph. But I also said 5 is a vertical asymptote. And a vertical asymptote represents an undefined value on our graph. Oh, that's a horrible vertical line. It's a good thing I'm going to erase that in a minute. But that undefined value on your graph is at 5, and the point 5 comma 0 is on our graph. This obviously doesn't make sense because we're saying at x equals 5, the function's undefined, and at x equals 5, the function is defined as 0. So therefore, this is a contradiction. And this contradiction we have here is the definition of where a whole occurs on a graph. Your graph will have a whole when something is both a 0 and a vertical asymptote. It can't be both. So we say there's going to be a whole in our graph at x equals 5. And some of you may have even wanted to do this when you factored back to our simplifying of rational expressions. And that's what makes the whole occur, is that fact that it can cancel. Now, we don't do that when we graph. We don't actually cancel things out. But that is why the whole occurs, because it is actually something that would be canceled out, but it also still makes the original function 0 on top, and it still makes the original function 0 on bottom. So therefore, it can't just disappear when we're talking about the graph. So let's look at how this affects a graph. So we know there is a vertical asymptote at 2. We'll see if I can draw a little better dotted line this time. There we go. At x equals 2, we know there's an undefined value. And what we talked about last time is how graphs approach these asymptotes but never touch them. So we know our graph's going to approach this asymptote and it's going to approach this asymptote. We also know we have no zeros in this function. So our graph is never going to cross the x-axis. So we could, at this point, start plugging in values. If you plug in 0, you get this. If you plug in 2, if you plug in 1, you get this. And we could put all those points on our graph, and we could figure out what's happening around the asymptotes and draw the graphs. But in order to save time, we're going to utilize technology. So we're going to go to Desmos and look at this graph, and also look at what a whole will look like on Desmos. All right, so you can see I've switched my screen for you here and I've gone to Desmos. You should all be familiar with this. Just a little tip for how to do this. You notice over here in my typing area, when I went to type in the rational function, in order to make a fraction occur, you have to put the top in parentheses, then hit the division bar. If you would do the top in parentheses and hit division, it automatically creates a fraction for you. So our graph looks like this, and this is good. It's matching with our work. We have a vertical asymptote at 2, but we also said we had a hole at 5. But when you look at where x is 5, it doesn't look like anything is happening there. But when we start tracing this function, and I get to 5, look what happens. You all of a sudden see my dot goes from a filled in red circle to an open red circle because at the value x equals 5, it is undefined. So that's how we're going to draw a hole in our graph. We're going to draw that hole by putting an open circle in our graph at 5. So let's go back to our screen and use what we see here to draw in our graph. So our goal is to be able to draw the best graph we can from the critical information we've taken from the equation and mixing it with the information we have here. All right, here we go. So we said our graph is going to look like what we saw on Desmos. So I'm going to look and I'm going to see over here we're below the axis. We come along and then approach the asymptote. On the top we do the same thing, except I have a little issue. I'm going to leave a little blank space there at 5, and I'm going to put in an open circle to show that this function is undefined at 5. It has a hole in the graph. We call that a point of discontinuity. All right, let's look at a higher level example now before we go on to the rest of our homework. All right, so we've prepared kind of the ultimate example here. So we've gone ahead and made this into the largest possible, for the amount of work we're going to do, example. So on top, you recognize we need to factor because that's where we've started with everything we've done in this entire unit. In order to get my critical information, my zeros, my asymptotes, and my holes, I need factored form. X minus 4 times x plus 3. Negative 4 plus 3 is negative 1. Negative 4 times 3 is negative 12. On bottom, I notice an x cubed, so that tells me I'm probably going to take out an x first. X squared plus x minus 6. But then we recognize that we have a parenthesis here that can be factored further. Numbers that add to 1 and multiply to negative 6 are going to be 3 and negative 2. So I can factor this down to the top staying the same, x minus 4, x plus 3, and on bottom, x is still there, but I can change what's in the parentheses to an x plus 3, x minus 2. All right, so we have zeros at x equals 4 and x equals negative 3. That's from looking at the top of our fraction. The bottom of the fraction says you have vertical asymptotes at 0, negative 3, and 2. Now I need to recognize, are there any holes? We look, yes, there is a value that is both a 0 and a vertical asymptote. That is not possible. So I eliminate those and I say at negative 3 we have a hole because you can't be both defined and undefined at the same time. All right, so we put all that information on the graph. We have a 0 at 4. We have a vertical asymptote at 0 and a vertical asymptote at 2. and we will put a hole at -3, but we can't do that yet because holes fall on the actual graph. So I need to have the graph there before I can make a hole. So let's go to Desmos, and I'll pause it here while I type it in to save a little time. So here you go. I typed this in. Like I said before, you've got to put a parenthesis around the top in order to make a fraction. And now that I've got that, I can look at my graph here. And again, this also confirms your work. There clearly is a vertical asymptote at 0 and a vertical asymptote at 2. And we approach this way, we approach over here. But in the middle, you notice we kind of have this parabola-like shape. And if you have two vertical asymptotes, in between them, one of two things is going to happen. It's either going to be a parabola-like shape, or it's going to come down and go out, kind of like in the top, out the bottom kind of thing, looking something like a cubic function in the middle. So let's go ahead and put this information on our graph. So we said on the left side here, we are up here near 0, we come through and go down and out, approaching the asymptote. Now you notice I left space here because this graph has a hole at -3. So I left a little open space when I drew my graph, and then I put in the open circle showing we're undefined at that one point. We have a point of discontinuity at that one point. Ooh, that was not my best one. It's actually supposed to stay closer to 0, but we're sketching the graph the best we can with our critical information. And then finally, we said we had kind of a parabola here in the middle, and so it looked kind of like that, where we are approaching the asymptote, approaching, but never touching. All right, this is your homework for today. You're going to try to actually sketch graphs. Again, if you need graph paper, I have some sitting in the front entryway of the school. You can swing by and grab some whenever you need. Have a great day.